Okay, so this video is going to cover Introduction to Electricity Part 2, and what we're going to be covering is the difference between series circuits and parallel circuits. So last time we talked about Ohm's law, and Ohm's law showed the relationship between voltage, current, and resistance, and you can show that three different ways depending on what you're trying to solve for, right? So if you have two of these values, say it's current or resistance, then you can solve for the voltage. Okay, so like I said, we're going to be talking about the difference between parallel and series circuits. And a series circuit has components that are connected end to end. Okay, so in this example, we have 4 different components. And a component can be a resistor or it can be a battery. And there's only one single path for the current to flow, right? So in this case, the current can only flow in one direction. In a parallel circuit, both ends of the components are connected together. So like here's component 1, 2, 3, 4. So both of these components are connected at one end. 2 and 3 are connected here, and 3 and 4 are connected here. So the current can actually flow, the total current can actually flow this way, can flow that way, flow this way or that way, this way, that way. So there's multiple paths that the current can flow. Okay, so when we talk about series and parallel circuits, we need to look at the relationships that exist between voltage, current, and resistance for each of the different types, because it's very different. So this is an example of a series circuit, okay? So here's the battery. This is the voltage here. Remember, this is the positive, this is the negative side. And each one of these squiggly lines represents a resistor. So we have 4 different components here, okay? And Kirchhoff's voltage law says that the voltage through resistor 1, the voltage through resistor 2, and resistance 3 equals the total voltage of the battery. So let's say the battery is a 9-volt battery. Then the voltage, if we were to measure it through resistor 1 plus 2 plus 3 would equal to 9 volts. Okay, so that's what Kirchhoff's voltage law means, and this is applicable for series circuits. When we look at parallel circuits, and this is an example of a parallel circuit, and remember, here's the battery, and then we have our resistor 1, resistor 2, resistor 3, and the components are connected at their ends, right? So for a parallel circuit, both ends of the components are connected together. So here we have our voltage connected to our resistor. Resistor 1 is connected to our resistor 2, and number 2 is connected to resistor 3. Okay, so Kirchhoff's current law says that the total current in a parallel circuit equals the sum of the individual branches. All right, so let's take a look at what that means. So essentially, the total current that's going through the battery, if we call that IT, right, it flows this way. Then if this is R1, and this is R2, and this is R3, then the current through R1, we can say that's I1. The current through R2, we call that I2. The current through R3, we'll call that I3. When these add up together, right, when they all meet, then that gives you your total current. Okay, so I1, so in this case, I total would be I1 plus I2 plus I3. And that's what Kirchhoff's current law is. Okay, so a series circuit says that there's only one path for the current to flow. So if we remove any component within that circuit, then we will not have a working circuit. Okay, so in this case, we removed a light bulb and the other light bulb does not work. Parallel circuits operate a little bit differently. If you remove a component, assuming it's not the battery, then you can still have another working component. So here, think about your Christmas lights, right? So if you buy Christmas lights and a bulb goes out and the whole strand goes out, then you have purchased Christmas lights that operate in series. If you lose a light bulb and the rest of them still work, you have purchased Christmas lights that operate in parallel. Okay, because here, if you lose a bulb, the other one still works. So there's multiple paths for the current to flow. So here's IT, which we call current total, it can't go this way, but it can still go this way. You can also have combination circuits, right? So you can have series and parallel. So you can see here that 1 and 3 operate in series. Okay, so if we remove bulb number 2, then we can see there's only one path for the current to flow, right? So in this case, if we remove bulb 3, then bulb 1 would not work. Okay. Now bulb 2 and bulb 3 operate in parallel, right? So if we remove bulb 3, 1 and 2 will still work. Or if we removed bulb 2, 1 and 3 would still work. Okay, so as long as we don't break the circuit completely where current cannot flow. Okay, so now I want to show you a simulation that I think will help you to better understand what's going on within the circuits. And you'll get to play with this simulation yourself, and you'll get to do some exercises. And I think this will help to understand the different types of laws and relationships that are going on within these two types of circuits. So the top circuit represents a series circuit, and the bottom circuit represents a parallel circuit. Okay, so one of the things, let me remove this. One of the things that we notice here is that in a series circuit, all of these little circles, which represents electrons, okay, so this is the electron flow, they're all moving at the same speed, okay? So that means that the current is going to be the same throughout a series circuit, right? So it doesn't matter how many components you have in there, the current will always be the same, okay? Doesn't matter if I have 1 bulb, 2 bulbs, or 3 bulbs. Now, in a parallel circuit, you can see that these electrons are moving at different speeds depending on where you're looking. So coming from the battery, which is the current total, splits off into 2 branches that move a lot slower than the current that's actually before the breaking of the branches, okay? And then the 2 branches combine here, and then it returns to its normal speed of 1.8 amps. So this goes back to Kirchhoff's current law for a parallel circuit, that you should add the currents for the different paths to get the total current, right? So with bulb number 1 current plus bulb number 2 current would actually give you the total current of 1.8 amps. So if we were to measure the current through each of these different bulbs, we would see that each one operates at 0.9 amps. So 0.9 plus 0.9 gives you 1.8 amps. Okay, the other thing to notice is resistance. Okay, so earlier we said that each bulb can represent a resistor, right? So this particular circuit here, we have 1 bulb. Now, if we were to add another bulb, okay, then we can see the electrons are no longer operating at 0.9 amps. Since we've added extra resistance into the circuit, it's actually cut the amps in half, and the bulbs aren't as bright, okay? So that tells you that for a series circuit, you add up the resistance, okay? So the resistance of R1, of bulb 1, plus the resistance of bulb 2 gives you the total resistance in the circuit itself, okay? Now, for a parallel circuit, resistance is a little trickier, okay? So you're still adding up the resistance, but it's going to be a fraction of what it would be for the series circuits, okay? And that brings us to this not so user-friendly equation of resistance total is equal to 1 over 1 divided by R1 plus 1 divided by R2 and so forth. And we'll look at that a little closer, but just know that the resistance is you still add it up, but it's going to be a fraction of what it was for a series circuit. Now for voltage, voltage is a little bit different for both of the different types of circuits. So this is a multimeter here. Now we know that this battery here operates as a 9-volt battery, okay? So what that tells us is, remember, for a series circuit, Kirchhoff's voltage law, you add up the voltages. So let's see what the voltage is going to be across our first component, this light bulb. It says 4.5 volts. the voltage across the second component is going to be 4.5 volts. What about both of them? 9 volts. So that tells us, that proves Kirchhoff's voltage law that says you add up the voltages for each of the components to get the total voltage in that circuit. Okay. Now parallel circuits operate a little bit differently. Okay, so you don't add up the voltages because, again, remember, think of the Christmas lights. If I remove a bulb, it doesn't make the voltage going through my other bulbs any more than what it was. So let's prove that, okay? So the voltage going through the first bulb is 9 volts. The voltage going through the second bulb is 9 volts. So what happens when I remove this light bulb? It still stays at 9 volts, okay? So what that says is that the total voltage is going to equal to the voltage of component 1. It's going to equal to the voltage of component 2, and then depending on how many you have, okay? So you don't add them, they're going to be equal amongst all the components. Okay, and again, you'll get to play with this a little bit later and do an activity to help you to better understand the two different types of circuits. Okay, and this is just a summary of what I just discussed. Okay, so for a series circuit, the current flowing through each component is going to be equal. All right, so a series component, the current flowing through each component is going to be equal. And then total voltage, you're going to add up the voltages, right? So V total going through the battery is going to be equal to the sum of the voltage drops across all of your components. So remember, voltage drop across bulb 1 plus voltage drop across bulb 2 equal to the 9 volts. And then the same was also true for the resistance. The resistance is also add up. So resistance total would be the resistance across bulb 1 plus the resistance across bulb 2. And if you keep adding bulbs, then the electrons will slow down even more and your bulbs will get less bright. Okay, so for a parallel circuit, remember the voltage across each component is equal. So think about the Christmas lights, right? So the voltage across every Christmas light is going to be the same. It doesn't matter if you remove one or add one. And then the sum of all the currents in each branch is equal to the total current. So remember how we added each of the different branches, and that equal to the total current going through the battery. And then this is this resistance total equation that I was mentioning earlier that's not very user-friendly, but this is what it is, and it's a fraction equation. So R total would be 1 over R1 plus 1 over R2 plus 1 over R3, right? So you would, whatever the resistance across that first bulb would be, second bulb, and then the third bulb, and that would give you the total resistance going through the entire circuit.